Good morning, students. Mr. Carver here. Today we're going to be doing section 9.5, area and arc length of polar graphs. If you recall back in the day when we were looking for the area between a function, say f of x and the x-axis, if you recall what we did was we used rectangles, something like that. Finite number of rectangles. We actually found the area of those rectangles, added them together, and we got a very rough estimate of the area between the curve and the x-axis. And then we engaged in integration, which took those rectangles, forced them to be infinitely thin, and what we came up with was an estimate that was so close that it was actually no longer an estimate. We're going to be using the same technique in section 9.5, except instead of using rectangles, we're going to be using these things called sectors, which are really just pie slices. So let's take a look at a common shape here. R is equal to, let's do 2 plus 2 cosine theta. Actually, you can think of that as a warm-up. Why don't you go ahead and graph that quickly. This is a cardioid pointing in the positive x direction, 4 units out. So I'm going to get something like this. Conjugate x is 2 up, 2 down, point of the shape being 4 units off to the right, which gives me my cardioid. Now, again, I'm going to be using sectors or pie slices to come up with this area, and I'm going to exaggerate this slightly. So my first pie slice might look something like this, goes from here, and just like we did when we first started working with rectangles, I'm going to use wide pie slices. So I might get something that looks like that. My next pie slice might look something like this, all equally wide, and what I would then do is add the areas of those pie slices together and get a somewhat terrible estimation of the area inside that cardioid. Then obviously what we're going to do, since we're already familiar with integration, is we will use integration to force each one of these pie slices to be infinitely thin. And the thinner those pie slices are, the more close my estimate will be to the actual area inside that cardioid. So let's talk about the area of a sector. And you can think about the area of a sector as just being a portion of the area of a circle. So for instance, if each of these thetas inside these pi sectors were 36 degrees, then this would be 1/10 of the area of the circle, each one of the pi slices. So I'm going to take theta over 2 pi, and I'm going to multiply that by the area of a circle, which of course is pi times radius squared. Those pi's cancel, so the area of my sector then can be reduced to 1/2 times theta times the radius squared, which could be generalized using summation notation. Don't panic, we're not going to have to use that. As 1/2 the change in theta of the ith interval times f of, or the radius of theta, the ith angle there, that quantity squared. And then, of course, we don't want to use summation notation because we don't need to any longer. Now we have a new notation for it and a new technique, and we will use this notation in blue. Now, if you think about this, the change in theta is going to be infinitely small. That change in theta now will be noted by d theta. My f of theta squared will be this, and of course that is nothing more than r squared. R will be given to you in the problem. And then lastly, the interval of integration will go from the small angle to the large angle. It's alpha and beta in this case. This is the notation, or the formula rather, for finding area inside a curve. So now let's go ahead and apply it to the formula that we're working with, this cardioid, 2 plus 2 cosine theta. All right, and I think that it's probably best to use symmetry on many of these because while this is a fairly straightforward example, they do get more complicated. So to get my head around where I'm at on this curve, I'd like to start with a quick r theta table just to double check so that I know where I'm at on the shape as my theta increases from 0 all the way around to 2 pi. So if I plug in 0, it puts me at 4 on this curve. So at 0, I'm right there. I then increase all the way over to pi. And when I plug pi in there, that's going to put me at 0. And just to make sure that I'm good here, when I'm at pi over 2, that's going to put me at 2 on the curve. So as I progress, my theta rather progresses from 0 to pi over 2 to pi. My r's go from 4 to 2 to 0. They're going to decrease. So it goes from 0, from 4 rather to 2 to 0. So if my theta increases from 0 all the way over to pi, my r's go from 4 to 2. Now, you do have the option in this case to go all the way around to 2 pi, and 2 pi will take you all the way back around to 4. So you have two choices. You can integrate from 0 to 2 pi, or you can integrate from 0 to pi and double it. So I'll write them both down here. So if I do, using symmetry, right, I'm going to just take the top half of this cardioid, I'm going to double the area, and the area from 0 to pi, my r is 2 plus 2 cosine theta. We're going to square that, d theta, because that's the formula. That will give you the area of the top half, and then you are doubling it, of course. So that'll give you the area inside this cardioid. Now, if you wanted to go and do the entire shape, you would not double it. You take 1/2. You would go from 0 all the way around to 2 pi of 2 plus 2. It'd be nice if I could write. Let me try this again. 2 pi. This is 2 plus 2 cosine theta, the quantity squared, d theta. Either one of those is correct. Now, I did mention using symmetry. Probably makes this process a bit easier. Let me give you an example of what I'm talking about now. You can also regard this as a bit of warm-up. If you'd like to hit pause and then sketch this quickly, hit play again when you're ready to go. I'm going to do it now. You've got a 4-petaled rose. I know it's 4-petaled rose because my n rather is even, so I double that. I also know that my length of each petal is going to be 1. That's my a value out front. Symmetric, of course, then to the x-axis. 2 ways to draw a 4-petaled rose symmetric to the x-axis. The first would be somewhat of a T shape, something like that. And the second would be something of an X shape, something like that. Easy for me to draw. So again, you've got to determine which one this is. A quick r theta table will help you get through this. If I plug in 0, and I'm going to pick 0 because that is the x-axis. I know it's symmetric to the x-axis. I take 0, plug it in there. That's 2 times 0. That's 2. Excuse me, 2 times 0 is 0. Cosine of 0 is positive 1. That puts me out here at positive 1. It means it must be this shape right here. All right. All right, kind of horribly drawn, but you have a 4-petaled rose symmetric to the x-axis. This is, in fact, the graph of cosine of 2 theta. And then I'm looking for the area maybe inside one of the petals. Again, if I do a quick r theta table, if I've got my r theta, and I plug in 0, we already know that I'm out here at 1. So, pointing in the 0 direction, I go 1 unit out. Now, it might be nice to know what r needs to be in order to get back to 0. I'm thinking it's probably pi over 4, but if you're unsure, you can either just plug it in and just double check that. So why don't we go ahead and do that. Pi over 4 gives me the cosine of pi over 2. That is, in fact, 0. So then I know that as my theta goes from 0 to pi over 4, my r's decrease from 1 to 0. Thinking out, I trace out the top of this first leaf right here. That's what I'm getting. So if the question said, find the area of one petal, I can use symmetry. I could go from 0 to pi over 4 and then double it. If I was looking for the area inside all of the petals, I could go from 0 to pi over 4 and then multiply that by 8 because there are 8 of those half petals. I hope that makes sense. Now, if this bothers you, you're unsure about that, you could always just set the original equal to 0, cosine of 2 theta. I'm going to arc cosine that. I have 2 theta is equal to, what is this, pi over 2, 3 pi over 2, 5 pi over 2. Just write a few out, then divide them all by 2. Theta is equal to pi over 4, 3 pi over 4, etc. Really, this is the first one you're looking at. It's the first one after 0 as you increase around the wheel in the counterclockwise direction. All right, so let's say I'm just looking for the area inside one petal. So I'm going to double it. I'm going to use symmetry. I'm going to take this times 1/2 the integral from 0 to pi over 4 of the cosine, rather, of 2 theta, quantity squared d theta. All right, those cancel. And just a little review from back earlier in the chapter, cosine squared of 2 theta, you're going to use a power reduction. Right? This is really the area from 0 to pi over 4. Power reduction of the cosine of 2 theta, that is going to be 1 plus the cosine of 4 theta over 2 d theta. I'm going to split these up. I get 1/2 0 to pi over 4 of 1 d theta plus 1/2 the integral of the cosine of 4 theta d theta. The first one just gives me 1/2 theta, evaluated from 0 to pi over 4. And the second one, I'm going to use u substitution. My u is going to be 4 theta, du is 4 d theta. Bring the 4 over to the other side. That is 1/8 the sine of 4 theta, going from 0 to pi over 4. I'll leave the evaluation up to you. That actually will give you the area inside one of those petals. All right, guys, just a few more examples, so hang in there. Let's say I was looking for the area inside this limison. Actually, go ahead and sketch this. Hit pause, sketch it, and then hit play again. This is what you're going to get. Like that. Cardioid pointing upward, positive y-axis. The point is 6 units out, the inner loop is 2, conjugate axis is 2 each way. All right, now, let's say that I was looking for the area inside the outer loop and outside the inner loop. All right, now I did say that it's important to have like spatial orientation as you look at this. So if I do an r theta table, and I plug in pi over 2, and I plug that in there, that's going to put me at 6. So if I'm pointing at pi over 2 direction, that puts me right here on the curve. Now, if I go all the way to 3 pi over 2, that puts me at -2 on the curve. So essentially what I get is something like this. I start at pi over 2, my thetas start increasing, my r's are decreasing, getting smaller and smaller until they get all the way to 0, but then I need to continue until my theta increases to pi over 3, putting me right there on the top of the inner loop. Again, that means as I increase from pi over 2 to 3 pi over 2, I'm going to get this series of dots for which my r steadily decreases from 6 all the way to -2, which means at some point in between pi over 2 and 3 pi over 2, my r value must be 0. And that's where I have to split this problem. So to find that angle, if I take my original r and I set it equal to 0, 2 plus 4 sine theta. I subtract 2 and divide by 4. That gives me -1/2 is equal to the sine of theta. My theta is going to be equal to 7 pi over 6 and 11 pi over 6. This is the one I'm looking for. It is the angle between pi over 2 and 3 pi over 2 for which my theta is 0. So let me draw this quickly for you. 7 pi over 6, I know this is not to scale, but 7 pi over 6 is the angle for which the r's transition from positive to negative. That is, it stops tracing out the outer loop and begins to trace out the right edge of the inner loop. All right, now the reason this is important is because remember, you are finding area with sectors or pie slices. So if I start finding the pi slices on the left-hand side of this outer loop here, what I'm going to be getting is this. If I integrate from pi over 2 to 3 pi over 2, I will be getting the sum of those pi slices. And one thing you notice about those pi slices is that they move through, or they pass through that inner loop. That's area that I do not want. So let's just start with the green area right now. And I'm going to use symmetry, so I'm going to double this. And I've got 1/2 my integral from pi over 2 to 7 pi over 6. It goes from here just to right there. That is going to be the left-hand side of the outer loop. This is 2 plus 4 sine theta, the quantity squared d theta. Now, this is giving me too much area because those pi slices or sectors have passed through the inner loop. I then need to take them out. Now, according to my r theta table, I know that when I plug in 7 pi over 6, I'm at 0, and I also know that when I'm at 3 pi over 2, 3 pi over 2, I'm at -2. That means if I progress from 7 pi over 6 to 3 pi over 2, I'm going to be getting the pi slices that fill in the right-hand side of my inner loop. And I'm going to double that. So I'm going to take out then, again, I'm going to double this. This is 1/2. I'm going to integrate from 7 pi over 6 to 3 pi over 2 of 2 plus 4 sine theta d theta. That second integral backs out the inner loop. So again, this is two sides of the outer loop, or double rather, the area on the left-hand side of the outer loop. And this is double the area of the right-hand side of the inner loop. The green is what is more than I need. Once I take out the red section, I get what I need. The difference of those two integrals is the area inside the outer and outside the inner loop. Now, for most of these, I'm going to have you just set these up, but if you were to actually integrate this, you'd need to FOIL these out, right? Because you've got a quantity other than x raised to a power, use power reduction in there, etc. It's kind of a long process. So much like chapter 6, you're going to be setting up most of these. All right, so the second portion of this section is they're actually going to give you two separate curves, and they're going to look for common area within them. So let me give you an example of that now. So find the area common to r equals 2 and r is equal to 4 sine of theta. You might want to pause this, maybe sketch these, and I'm going to do it now. All right, so here's what you got. R is equal to 2 is a circle centered at 0 with a radius of 2. That's this lower circle here. The second one here is a one-petaled rose, 4 units long. Now, I should mention this. If you have a single-petaled rose, you probably have noticed this as you go through some of the conversion problems from section 9.4. A single-petaled rose converts into a circle equation. So if you draw a single-petaled rose, make it with a single circular petal, and that is the upper circle in this case. So I'm looking for the area common to these two shapes, which means I'm looking for this blue shape right here. That's what I'm looking for, the common interior area. Okay, now, remember, you're finding area within these shapes using sectors or pi slices. So it's important to, first of all, find the intersection points between these two curves. We're going to do that right now. Because remember, as I'm using sectors, I'm going to transition from one shape to the other to define the length of that sector. All right, so let's first of all find the points of intersection. If I set 2 equal to 4 sine of theta, divide by 4, I have the sine of theta is equal to 1/2. That means my theta is equal to pi over 6, 5 pi over 6. So what I'm looking for is that angle right there and that angle right there. That's where the two curves intersect each other. Now, let me redraw this graph just in Q1 because, again, I'm going to use symmetry here, just like we did before. All right, so there are the two circles, or portions of the two circles, that lie in Q1. This is my pi over 6 right here. And again, I'm looking for just the common interior, the common interior in this case, only in Q1, excuse me, that's not right. Common interior in Q1 is this area right there. All right. So I'm using pi slices. So when I start to increase from 0 to pi over 6, I'm going to use this upper curve. I'm going to use this circle right here because that R will define the length of each one of my sectors. So if I were to draw them in, it'd be something like this. These sectors will first be defined by that upper circle. So I'm going to use symmetry. Remember, I've got two sides of this, so I'm going to double this. This is going to be 1/2 the integral from 0 to pi over 6 of 4 sine theta, quantity squared, d theta. I'm going to add to that then. I just need to add this additional sectors defined from pi over 6 to pi over 2. And I'm going to do these in orange. That'll be these pi slices right there. Add that. Again, I'm going to use symmetry. I've got two sides of this. This will be 1/2 the integral then from pi over 6 to pi over 2. But now I'm going to use my other equation. That is 2 the quantity squared d theta. And again, because I'm emanating from the pole out to this curve right here, which is r is equal to 2. But again, it shifts from 4 sine of theta to 2 as I increase from pi over 6 all the way up here to pi over 2. The combination of these two areas gives me the common area, common interior to r equals 2 and r equals 4 sine theta. All right, guys, thanks for hanging in. I know this is a long section. The very last thing we need to talk about today is arc length. All right, the last section is arc length and surface area. Surface area for a bonus because they're super closely related to how you do it in parametric. All right, so let me give you the formulas here. This will all be calculator work. I'm not going to have you integrate these by hand. All right, so your formula for arc length is the integral from alpha to beta that is going to be given in the problem, much like the parameter interval was given in section 9.3. That is then times the square root, or rather of the square root, of f of theta the quantity squared plus f prime of theta the quantity squared. This is not rectangular slope, but simply the derivative of your r equation. And I'll show you how to do that right now. If you have r is equal to 2 minus 2 cosine theta from 0 to 2 pi, and I'm looking for the arc length from 0 to 2 pi, you're just plugging it into your calculator. I'm going to go from 0 to 2 pi. This is the square root of your r, which is 2 minus 2 cosine theta, the quantity squared. Type it in just like that, plus then the derivative of r. The derivative of r with respect to theta is 2 sine of theta, the quantity squared. Again, I'm just deriving this expression right there, and that's d theta. Now, when you plug this into your calculator, you want to be in radian mode. Super important. Those bounds are radian. So radian mode, make sure you check that. Punch it in exactly as you see it. You're not going to be using thetas, though. You're going to be putting them in terms of x. Doesn't matter. The calculator doesn't care what variable you use. So 2 minus 2 cosine x, the quantity squared, plus 2 sine x, the quantity squared, dx. This part goes into y1. It is second to calculate, number 7, integrating from 0 as your lower bound, 2 pi as your upper bound. It will give you a decimal answer. That's what you're looking for. Lastly, I think it would make sense that if we're looking for surface area, you need to take the arc length and multiply it by 2 pi radius, 2 pi r. And I hate to use r, but it is 2 pi times the radius. So let me give you an example. Let's say you're going about the y-axis. This is going to be the integral from alpha to beta. That is going to be 2 pi. Now, if you're going around the y-axis and you've got something that looks like this, going around the y-axis, your radius there is nothing more than x. And x, if you recall, is r cosine theta, times then the square root of what you had before. This is f of theta, the quantity squared, plus f prime of, theta, the quantity squared d theta. All right, if you're going around the x-axis, sometimes known as the polar axis, you're going to integrate from alpha to beta. And again, I think it would make sense that if you're going around the x-axis, your radius will just be y, that is r times the sine of theta, times then the square root of f of theta, the quantity squared, plus f prime of theta, quantity squared. You only need one set of parentheses on the left-hand side there. You get the idea. What the? That is not a very fine eraser. Now we're cooking. All right, so it's either 2 pi x or 2 pi y, depending on what your radius will need to be. So, quick example. Let's say I've got r is equal to sine theta. Incidentally, that is a one-petaled rose, 1 unit long, and remember, a one-petaled rose is a circle. Going about the polar axis, that is the x-axis, from 0 to pi. You're just plugging it in. I'm going to go from 0 to pi. If I'm going around the x-axis, that is going to be 2 pi times y. That is r sine theta. My r is the sine of theta. I multiply that by the sine of theta. This will be then times the square root of sine of theta squared, plus, continue down here, that is going to be the cosine of theta squared, d theta. All of this, except for the d theta, all of this goes into y1. You're going to use x's instead of thetas. Radian mode, second calc 7 from 0 to pi, enter. That's what you need to know. Guys, thank you so much for hanging in there. I think we've just about killed off section, or chapter 9 rather. Again, this is a big section. We'll spend a couple of days on this review, and we'll be testing it over it soon. Thank you, guys.